Okay. I'm going to give a little bit of time for folks to filter in here because I know you've gotten a bit used to the other system. But we are back to our normal thing today. And today is an exciting day, as we left off after learning the comparison tests last Friday. So today we're going to start talking about the alternating series test. One of the reasons this section is exciting is because from 11.2 through 11.4, we couldn't really get any idea for the actual value of the infinite series we were playing with unless it was a telescoping series or a geometric series. But today we're going to get a technique that allows us to estimate the size of some other series. So broaden our horizons a little bit. And forgive me if I'm a little bit sleepy. I'm definitely jet lagged. I got in late last night after way too many hours of traveling. But we are going to go ahead and get started here. I'll launch QCam. Okay, there it is. All right. Yeah, that's good. You can close. So this is Calc 2. I might have to change colors here. This pen seems like it doesn't want to cooperate, but we'll see as we go. So today, yeah, no way. Today, we're going to talk about the alternating series. There's an alternating series test and an estimation theorem. And so we're going to be talking about alternating series and estimation of sums. This is section 11.5. Before we get into the actual material here, because I know that lately you guys have been working with the pre-recorded lectures and that's not the same level of interactivity, I just want to do a quick recap of the basic concepts. Cool. Series are objects that look like, usually I'll give them the name capital S, and they're written with this big sigma. And n might run from 0 to infinity or 1 to infinity or something like that. And inside we have these things that we call an usually. And that whole capital sigma thing is shorthand for a1 plus a2 plus a3 plus a4 plus a5, going on and on and on forever. And we say these converge. We say that the series S converges if its sequence of partial sums which is the sequence Sn defined by saying S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3 and so on. S sub capital N is A1 plus A2 plus A3 all the way out to AN. So the idea is that the SNs are all finite in length. And we could write this one in the sigma notation as the sum from 1 to capital N of A sub little n. We say that the series S converges provided its sequence of partial sums Sn defined this way is a convergent sequence. So this was the basic idea of the things we've been working with. And from 11.3 and 11.4, you have a few new tests that you can apply to certain series to tell whether or not they converge. Some of those tests are fairly weak, like the test for divergence, that only tells you on very rare instances where the ANs don't go to 0 that the series must diverge. But then you had stronger tests like the limit comparison test and the integral test, which were capable of telling you whether a series converged or not by comparing it or relating it to another object. So it is my sincere hope that you guys have been working hard over the last week and that we are comfy with the material of 11.2, 11.3, and 11.4. I will have a normal office hour today if you want to come by and talk about any of those things. And I'm working on getting through the emails. I cleared my inbox twice while I was out of town, but I'm fully aware that there are some messages that were sent probably after Friday that I haven't gotten to yet. So if you urgently need to see me, come by office hours. Otherwise, I'll be getting through that inbox over the rest of the day. So like I said, today is about alternating series, which are different than most of the series that we've seen so far. If you look back over all of the convergence tests that we've discussed so far, all of them in one way or another require that the series only have positive terms, right? They all say it differently. Like the integral test says that the related function has to be positive. Oh, but if the related function is positive, then the terms of the series are positive. The comparison tests just outright say that the AN and the BN or whatever have to be positive. An alternating series does not have only positive terms. So an alternating series, and that's what we're defining here, is a series in which every term changes sign. E.g., the series like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. This would be an alternating series because every time as you go term to term, we're changing sign, right? We go positive to negative, negative back to positive, positive back to negative, negative back to positive. So series like these are called alternating series, and these can usually be written as S equals sigma -1 to the n or n plus 1 times Bn. Now maybe here the n starts at 1 or starts at 0, it all depends. I'll say here it starts at 0, where the Bn's are positive. Right. Sometimes the power of -1 will be -1 to the n plus 1 or -1 to the n minus 1. But the whole idea is that you have a power of -1 that flips back and forth between positive and negative. Sometimes the series will start at 0, like I've written it here. Sometimes it'll start at 1 or 2, and you've seen that in the homework for other series problems. If I take the series above, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on, I can write that in sigma notation. There's a couple of different ways. When I look at that, what I see is that the terms look like 1 over n. Right? 1 over 1, 1 over 2, 1 over 3, 1 over 4. But they're flipping back and forth from positive to negative. So there's a power of -1 in here somewhere. I have to choose whether to start the series at 0 or at 1. If I'm going to say these are 1 over n, I cannot be starting this at 0 because then the first term would be 1 over 0, and my first term should be 1 over 1. So it's going to go from 1 to infinity. But then if I want to get the signs correct, I want this first term, the n equals 1 term, to be positive, the n equals 2 term to be negative. So rather than using -1 to the n, I should use -1 to the n plus 1. And this particular series has a name. This is called the alternating harmonic series. So here, Bn is just the 1 over n piece. Do we feel comfortable with the definition of an alternating series? We can recognize whether a series is alternating or not. And we can move it from the ellipses ... notation into the sigma notation and vice versa. All right. So then I'm going to give you the theorem, and I'll show you how to use it. Oh, there's a question in chat, yeah. You could use another negative number to the power of n to get the alternating behavior, but remember those can always be written. Yeah, so Nick asks a good question. What about using something like -2 to the n to get your alternating behavior? So the sum -2 to the n is an alternating series. If we write this out, this is -2 to the 0, that's 1, plus -2 to the 1, that's -2, plus -2 to the 2, that's +4, plus -2 to the 3, that's -8, plus -2 to the 4, that's +16, and then the next term would be -32, and so on. But you can write this as, in that form of an alternating series, there is -1 to the n times 2 to the n. And then here the series would still start from 0, go from n equals 0 to infinity. So you can still write this as -1 to the n times some positive bn's here. So bn in this case would be 2 to the n. And if you try to get your alternating series using something other than -1 to the n as the alternating bit, then that will be contributing something to the bn's, and it could hide something that you don't want hidden. So yes, in practice, it'll always be a -1 to the n, but sometimes you need to do some algebra to rearrange. Something like that, yeah, not necessarily a constant multiple here because the n's make these non-constant when you write them in the sigma notation, but that's the idea, yeah. Yeah, it's always -1 times something to the n in the sloppiest case. Okay. Theorem. This is your next convergence test. It's called the alternating series test. The alternating series test only works for alternating series. It says if S equals sigma, whoa, that's an ugly sigma, n from wherever to infinity, -1 to the n times Bn is an alternating series And remember, it doesn't need to start at 0. We could start at 1 or 2 or 3 and all this, the same stuff would still apply. If you have an alternating series where the BNs are a decreasing sequence, and 2, the limit of the BNs is 0, then S converges. My series. And again, could start at 1, doesn't need to start at 0, could start anywhere. So if you have an alternating series where the general term, the positive part of the alternating series terms, decrease to 0, that's enough to get the series to converge. And this is at first really counterintuitive because we've seen lots of series where the general term does go to 0, but the series does not converge. For example, the regular harmonic series, 1 plus 1/2 plus 1/3 plus 1/4. The general term there is 1 over n, and that does go to 0. But because that series isn't alternating, that's not enough to get it to converge. However, the first example that we looked at today, the alternating harmonic series, does converge. So a quick example and then a proof. So this is another way of writing that series we looked at in the first part of today's class right away. If you start plugging in some numbers, you get -1 squared over 1 plus -1 cubed over 2 plus -1 to the 3 over, -1 to the 4 over 3 plus -1 to the 5 over 4, and so on, which is 1 minus 1/2 plus 1/3 minus 1/4, and so on. This is called the alternating harmonic series. And you can see why. You remember the harmonic series is just the 1 over n series, so 1 plus 1/2 plus 1/3 plus 1/4. Here, this is the same sort of series, except every other term changes sign. So it goes 1 minus 1/2 plus 1/3 minus 1/4. And somehow that alternatingness changes things pretty dramatically. Let's run the alternating series test. The alternating series test applies because this is an alternating series. And it says that if the BNs are decreasing and the limit of the BNs is 0, then the series must converge. So here, what is BN? In this example we're playing with, what is BN? Yeah, the non-alternating piece of this, the piece besides the power of -1, that's the Bn. So here Bn is 1 over n, and that is a decreasing sequence. Why? Because n itself is increasing. And you may remember from that video last Wednesday on the integral test, the reciprocal of an increasing thing is always a decreasing thing. That's a lazy way to do it. Or you could take the derivative of the bn's and show that the derivative here, which is -1 over n squared, is always negative. The second condition here is that the limit as n goes to infinity of the bn's is 0. And in this case, the limit as n goes to infinity of the bn's is the limit as n goes to infinity of 1 over n, which is certainly 0. It's 1 over infinity, which is 0. Therefore, by the alternating series test, which I'll abbreviate AST, the series, we should write out what the series is so our reader knows what we're referring back to. The sum from n equals 1 to infinity, -1 to the n plus 1 over n converges. Right, so that's it. That's how easy the alternating series test is to use. You just have to show that the bn's, the positive, the non-alternating part of your series, decreases to 0. As long as that's the case, then the alternating series will converge. So it's much easier for an alternating series to converge than for a series of all positive terms to converge. That's the kind of shocking thing. Something about going back and forth between adding and subtracting allows the sequence of partial sums to converge more rapidly. And I'd like to explore a little bit why that's true. And the easiest way for me to do that is to prove for you the alternating series test. But there's kind of another thing here, and that's the estimation theorem. So I'm going to give you the estimation theorem, and then I'm going to give you a proof that shows why both of those things are true. Before that, though, any questions on this example, what we did here, how we were able to show that this series, the alternating harmonic series, converges? All feeling mostly good? Okay. So I'm going to give you the estimation theorem, then we're going to prove both things, and then we'll look at a couple other examples. Like the alternating series test, the estimation theorem I'm about to give you only works for alternating series. Thankfully, a lot of interesting series are alternating. This says if S is a convergent alternating series, then the absolute value of S minus Sn is always less than or equal to B sub capital N plus 1. And this might take a little bit of thinking to really understand. Remember, S is the actual value of the series. And Sn, this is the nth partial sum. Of the series S. So when you subtract those, what you're looking at is the error in the nth partial sum. It's how far Sn is from S. So this whole thing here altogether is the error in Sn. Again, you may need to think about this for a little bit. If I subtract two numbers and then put that in absolute value, that tells me how far the two numbers are from one another, right? Like the absolute value of 3 minus 10 is 7. And that tells me that 3 and 10 are 7 away on the number line. So the absolute value of S minus Sn, this expression right here, forget about the inequality for a moment, this expression right here just tells me how far Sn is from S. Now, S is what I want to approximate. I don't know the value of that series. Sn is something I'm capable of computing. It's a finite sum, right? Like I can write down S5. So this error tells me how far the thing I can compute is from the thing I want. This tells me that my error in my nth partial sum is no greater than the next term of the series. The estimation theorem here is used to tell you how large of an n you need in order to get your Sn close to S. So I'm going to give you the proof of the theorem. We'll prove actually both theorems at once. Proof of the alternating series test, AST, and the estimation theorem. So the picture I'm about to draw for you, once explained and understood, proves both of those things at once. The picture is in your textbook as well. So here's a number line. Well, it depends on what you're trying to do. So Nicholas asks a good question. How close should I be trying to get Sn to S? So maybe you know S, the full alternating series, represents some number, and you'd like to know the first 3 decimal places of that number. Then you want to make sure your error is smaller than 0.0005, right? Because if it was off by more than that, you would round up. So the answer to your question, Nicholas, is going to depend on what it is you're hoping to do. But I'll give you an example in a few minutes, which I hope will clarify. So let's imagine here that S is B0 minus B1 plus B2 minus B3 plus B4 minus B5, and so on. So that S0 is B0, S1 is B0 minus B1, S2 is B0 minus B1 plus B2, and so on. So here's the full infinite series. It's an alternating series. And here's the first few partial sums. S0 is the same as B0. But now, from B0, I'm going to subtract B1 to get to S1. So if S0 is way over there, then S1 is right here. And that's B0 minus B1. Now something cool is going to happen. I'm assuming that the BNs are decreasing. And that the limit as n goes to infinity of the BNs is 0, because those are the hypotheses for the alternating series test. What that means is that when I go from S1 to S2, I'm going to be adding B2, right? That's the difference between S1 and S2. S2 is the same as S1, just plus B2. So I'll be going to the right over here, B2 units. So to go from S0 to S1, we subtracted B1. From S1 to S2, we're adding B2. But because B2 is smaller than B1, under this hypothesis that the BNs are decreasing, I know that S2 will not be to the right of S0 over here, must be to the left of S0 over here. Because the amount that I'm coming back to the right is B2, and B2 has to be smaller than B1 because the BNs are decreasing. To get from S2 to S3, I move to the left by B3. But because the BNs are decreasing, B3 has to be smaller than B2. And this pattern continues. And we end up nesting our SNs until we arrive somewhere in the middle here, which is S. You really have to think about how this decreasing thing is important. The BNs decreasing is what guarantees that every time I jump, I'm jumping less and 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 less, which is what allows this nesting to happen. And the fact that the limit of the BNs are 0 is what guarantees that we actually come into some center point S. Like I said, your book has this picture. I'm going to flip over to your textbook in just a second here, because it looks a little bit cleaner in print. Some definition, here it is. Okay, so we move to the right and then we move to the left, but the amount we move to the left isn't as much as we move to the right because the BNs are decreasing. Then we move to the right again, but it's less than we just moved to the left because the BNs are decreasing. Then we move back, then we move forth, then we move back. So the back and forth movement is because the series is alternating. And the fact that these are getting kind of tighter comes from the fact that the BNs are decreasing. Finally, because the limit of the BNs are 0, the back and forth jump is going to get smaller and smaller and go all the way to 0, which is what guarantees that you have to come in towards some center point here, which is the full value of the series. So this picture has everything that you need. And I recommend that you think about this proof just through this picture, right? Draw this picture, think about it until it clicks. You can go through the proof that they have here. but it's not very enlightening. The picture really does have everything you need, and that is how I would encourage you to think of it. Now, like in all of these things, you're not responsible for the proof, but the proof will help you understand why you're doing what you're doing. If you think about it, this also proves the estimation theorem. What's the distance from S to S2? Well, that's this distance right here. That's guaranteed to be smaller than B3 because going from S2 to S3 jumps over S. So the distance from S to S2 is smaller than B3. The distance from S3 to S4, which would be right here, is smaller than B5, which is the distance we would be jumping back to get to this tick mark. This distance is smaller than this distance, just like this distance is smaller than this distance. So the distance from S to Sn is always smaller than B sub n plus 1. And that's it. Those are the two theorems proved just from this picture. So again, I invite you, you may want to look at this picture in the textbook because it is a little bit cleaner. But I want you to think about this until it clicks. It will click eventually. How do we use this estimation theorem? Or what do we care? Why do we care about the error size? Well, usually somebody specifies, like, I want the value of this series with so much precision. You know, I want the value of this series correct to 2 decimal places, something like that. So let's take a look. We observed earlier that the alternating harmonic series converges. Estimate the value of the alternating harmonic series, which is sigma n from 1 to infinity, negative 1 to the n plus 1 over n. Estimate this accurate to 3 decimal places. Let's see if we can do that. Well, here we know that S minus Sn in absolute value is less than or equal to B sub n plus 1. Bn plus 1 is 1 over capital N plus 1, because Bn is 1 over n. Remember, we mentioned that before when we proved that this series converges. So our nth partial sum is off from the total value of the series by at most 1 over n plus 1. To be accurate, to 3 decimal places, we want the error to be less than 0.0000, let's say 0.0001. Now in practice, this could actually not be enough. You might want 0.00001 or 0.00005. If you're off by 1 in the 4th decimal place, that could mess up the rounding in the 3rd decimal place. But as long as these first 3 are zeros, then the first 3 of your fellow, as long as you don't round it, will be accurate, will be correct. So we know that this is the error, and the error is smaller is smaller than 1 over n plus 1. So the error will be less than 0.0001 for sure if 1 over n plus 1 is less than 0.0001. All right, my error is known to be smaller than n plus 1, 1 over n plus 1. I want my error to be less than 0.0001. So I can say for sure the error will be less than 0.0001 as long as 1 over n plus 1 is less than 0.0001. We're using the transitive property of inequalities here. Since the error is less than 1 over n plus 1, and 1 over n plus 1 is less than 0.0001, the error will be less than 0.0001. So basically in these problems, what you do is you set bn plus 1 smaller than your desired error. Then you solve for n. Solving an inequality like this can be challenging. These inequalities are usually nonlinear. The easiest way for me to solve this one is to rewrite this number as a fraction. This is 1 over 10,000. Hundreds, tens, hundreds, thousands, 10,000s. And then I can use some properties of inequalities, like I can take the reciprocal on both sides, and that will flip the sense of the inequality. So this is equivalent to saying n plus 1 is greater than or equal to 10,000, which is equivalent to saying that n is greater than or equal to 9,999. So to estimate series S accurate to 3 decimal places, it suffices to use S sub 9999, the 9,999 partial sum, which is sigma n from 1 to 9,999 of -1 to the n plus 1 over n. Now this might not sound like a very useful thing because writing out the first 9,999 terms of this series is quite a lot, but it is something we can compute. So I'll go ahead and do this computation. Something we can compute exactly because it's finite. All right, so here it is. I'll just write out the first few decimals. This is 0.69319718. Okay. For reasons I cannot explain to you right now, but I will be able to explain to you very soon after we talk about power series, I know what the actual value of this alternating harmonic series is. The actual value of the full alternating harmonic series, the actual value of this full series is the natural log of 2. So let me say this. I know that S is ln2. So let's see how we did. Let's see how well we approximated. What is the actual value of the natural log of 2? .693147. I've got 0.693197. So not only did we get the first 3 decimal places correct, we got the first 4 decimal places correct, because the error in our sum could be off in the 4th decimal place only by as much as 1. So we allowed for an error of 1 here. And it turns out we did even better than that. Right? We ended up with an error of 0 in that place and an error of 5 in this one. So this is a really good, really accurate estimation. We had to use the first almost 10,000 terms of the series to get it, but still, this is a finite sum, so it can be computed exactly. This, by the way, is what your calculator does when you ask it for the natural log of 2, or the natural log of 5, or the natural log of any number that's not nice. It does a computation just like this. I'd like to go through this procedure at least one more time, where we prove that an alternating series converges, and then we apply the estimation theorem. And there's one other really famous example here that I'd like to use. So before I do that, questions on the use of this theorem, the estimation theorem? Yeah, so if I were to give you this on an exam, I might ask you for the minimal value of n and then not ask you to compute the series, right? So here getting n is greater than or equal to 9,999 didn't require any strenuous computation. So I could give you a problem just like this and then just, not care that you actually do this piece. Or I could give you a series that converges more quickly so that the n value is much, much smaller, and then I could ask you to compute this. Yeah, both ways could occur on a test. Other questions on this one? Yeah, I agree that nobody on an exam has time to write out nearly 10,000 terms of a series. That would be silly. Okay. So another famous alternating series like this, let's show that S equals sigma n from 0 to infinity, negative 1 to the n over n factorial converges, and estimate its value. Again, let's say accurate to 3 decimals. So same sort of thing. Only now, instead of an n downstairs, it's n factorial. And instead of starting at 1, it starts at 0. And instead of having negative 1 to the n plus 1 upstairs, it has negative 1 to the n. First, let's just see what the series S looks like. It's negative 1 to the 0 over 0 factorial plus negative 1 to the 1 over 1 factorial plus negative 1 squared over 2 factorial plus negative 1 cubed over 3 factorial plus negative 1 to the 4 over 4 factorial and so on, which is negative 1 to the 0 is 1, and 0 factorial is 1, so the first term of the series is 1. And then negative 1 to the 1 is negative 1. 1 factorial is also 1, so it's minus 1. And then plus 1 over 2 factorial. 2 factorial is 2. Minus 1 over 3 factorial. 3 factorial is 6. plus 1 over 4 factorial. 4 factorial is 24, and so on. And the first two terms eat each other up, they're gone. Similar to the last problem, for reasons I can't explain now, but can explain after we learn about power series, I know that S here is actually equal to 1 over E. Comes from power series. Which is the first topic after exam 2. So exam 2 goes up to power series, but does not get into them all the way. And then exam 3 is everything from power series on. So after exam 2, I'll be able to show you why this is 1 over E, but for now, I just want to show that the series converges and then estimate its value. And I'll compare that value against what my calculator says 1 over E is. All right. So first I need to run the alternating series test. Here, Bn is what? What are the Bn's in this alternating series? Good, 1 over n factorial. It's just the non-alternating part of the summand. So just like the thing inside the integral is called the integrand, the thing inside the sum, right? This is a sum. The thing inside the sum is called the summand. The non-alternating part, the part aside from the -1 to the n, that's the Bn's. So here that's 1 over n factorial. And we need to check or verify that the Bn's are decreasing. And in this case, there's lots of ways to show this. Yes, n factorial is increasing. So Bn, which is its reciprocal, is decreasing. This is not a case where you could work with the derivative, because the derivative of the factorial function you don't know. In fact, it's fairly complicated. It requires work with something called the gamma function to even talk about differentiating the factorial. So here, differentiating isn't really an option. Another way to show that Bn's are decreasing is to show that Bn plus 1 is always less than or equal to Bn. Now, in this case, that's equivalent to saying 1 over n plus 1 factorial is less than or equal to 1 over n factorial. And we have to verify that this is true for all n. So one way to do that would be to take reciprocals, which flips the sense of the inequality. And then we can write out the factorials. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And n factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And now you can divide both sides by this chunk. It's the same chunk on both sides. And if you divide both sides by that, you get the statement that n plus 1 is greater than or equal to 1, which is true. So two different approaches to showing that your BNs are decreasing, or really three different approaches. One of them is to say that your sequence is the reciprocal of an obviously increasing sequence. Now, n factorial, the factorial sequence, that's a sequence we know well, that is increasing. So his reciprocal, I can say comfortably, is decreasing. We could try taking the derivative of the BNs and showing that that derivative is always negative, but here the derivative of 1 over n factorial is very complicated, so we can't do that on this particular problem. The other option, Bn is decreasing, the sequence is decreasing, that means that if you compare a term that comes after Bn, Bn plus 1 should always be smaller than Bn. Like this says B3 is smaller than B2. And B4 is smaller than B3, and B5 is smaller than B4. That the next term of the sequence is always smaller than the term that came before. That's exactly what it means to be decreasing, right? That you get smaller as things go on. So you can prove this inequality is true for all n, or you can say that your sequence is the reciprocal of an increasing sequence, or you can take the derivative of the BNs and show that that derivative is always negative. Those are your three ways to show that a sequence is decreasing. In any case, this sequence is decreasing, right? It is both the reciprocal of an increasing sequence, and we can show algebraically that the sequence is decreasing. The other thing we need to check is that the limit of the BNs is 0. Well, here, the limit of the BNs is lim n to infinity 1 over n factorial. N factorial definitely goes to infinity as n goes to infinity. So this is 1 over infinity, which is 0. So yep, both of these are satisfied. Thus, by AST, the series S equals sigma n from 0 to infinity, negative 1 to the n over n factorial must converge. That's just the first part of this problem. The first part of this problem asked us to show that the series converges. So here is the AST work to show that the series converges. Any question on this part of the problem? Any question on what you would be expected to do if this were an exam problem? Okay, so finally, our estimation theorem. We know that the distance from S to Sn is always less than or equal to B sub n plus 1. And B sub n plus 1 here is 1 over capital N plus 1 factorial. So we need, to get Sn correct to 3 decimals, we want 1 over cap n plus 1 factorial to be smaller than 0.0001. And this might be mild overkill, but this guarantees that your first 3 decimals are correct and your 4th decimal is off by at most 1. Which could, again, if you're rounding, still throw you off in the 3rd decimal, but we'll guarantee that the first 3 decimals are correct. That's enough for us. Now again, 0.0001, that's 1 over 10,000. So this is the same as saying 1 over n plus 1 factorial is less than or equal to 1 over 10,000. And again, we can take reciprocals. But now we run into a problem. There's no nice way to undo the factorial function. If I'm trying to solve this inequality for n, normally we would want to get n alone, right? Which would mean like undoing the factorial. But there is no nice inverse to the factorial operation. It's a complicated operation, and we don't know a nice way to undo it. So from here, we're going to have to employ a little bit of guess and check. If capital N is equal to 2, then n plus 1 factorial is 3, factorial is 6. That's not bigger than 10,000. If capital N is equal to 3, then n plus 1 factorial is equal to 4 factorial, which is 24. It's still not big enough. If capital N is 4, then n plus 1 factorial is 5 factorial, which is 120. If capital N is 5, then n plus 1 factorial is 6 factorial, which is 720. But when n is equal to 6, then we'll have n plus 1 factorial is 7 factorial, and 7 times 720, we might be getting close there. Let's see. 7 factorial is 5,040, almost. So when capital N is equal to 7, then n plus 1 factorial is 7 plus 1 is 8 factorial, and this should be large enough. Yeah, 40,320. Plenty big. So what's the first value of n such that this inequality is true? Well, n equals 6 wasn't quite big enough, but n equals 7 was. So this is true provided n is bigger than or equal to 7, which means I could use S7. Means S7 is correct to 3 decimal places. And what is S7? Well, that's the sum from n equals 0 to 7 of -1 to the n over n factorial. Let's see what that is. -1 to the n over n factorial summed from n equals 1 to n equals 7. Here we get 103 over 280. Which in decimal form is 0.3678. 0.367857. So according to my theorem, S7, which is this number, or in decimal form, this guy, should be really, really close to the exact value of the series, 1 over e. Let's see what 1 over e is. Zero 0.367, and I'll write this down. 0.36787 blah, blah, blah. So let's compare them. My estimate based on this theorem using the partial sums is 0.367857. The actual value of 1 over e is 0.367879. So not only did we get the first 3 correct, we also got the 4th guy correct. And the 5th guy is off by only 2. So our actual error here is 0.00002-ish, which is incredibly good. NASA scientists would love to be using 4 or 5 figures, sig figs, in all of their computations, but often they settle for 3. So S7 is a really good estimate of the actual value of this series. If you are on a desert island and you needed the value of natural log of 2, or you needed the value of 1 over e, this is the best way to get it. At the moment, you wouldn't know that these series are outputting those numbers, and you wouldn't know how to find a series to output any number that you wanted like that, any weird number. But soon you will. After we've talked about power series, you will know how to do that. The point of section 11.5 is to do 2 things. First, to show you that there are series where not all the terms are positive and how those series converge. And that's what the alternating series test does, is it gives you some criterion that show you when those series converge. And second, to give you the tools you need to start estimating the size of a series. Up until now, we really haven't had any tricks for estimating series. And if we have a geometric series or a telescoping series, we know how to find the values of those exactly. But all the other series that you worked with in your homework last week, we had no way to estimate them. We didn't have a clue what they converged to. We just knew that they converged or knew that they diverged. AST is really nice in that it not only gives you an ability to say, yes, this converges, it also, through the estimation theorem, gives you the ability to say, and the value is about this. Like I could say with a lot of confidence that the value of the full series S that we just played with is about 0.367, and I would be correct. And it's that theorem that told me how far I needed to go in my partial sums to get those first 3 decimals, or in this case, first 4 decimals, correct. Yeah, Nick, so I'll respond to your email a little later today when I have some time. Okay, I think that is about everything I wanted to cover today. So I'd like to take a second here to just recap one last little thing. Because the alternating series test is not hard to use, but I don't want you to get confused. So AST, alternating series test, says, given a series, an alternating series with positive parts Bn, if the Bn's are decreasing, and the limit of the Bn's equals 0, then the series converges. the reason I'm reiterating this is because I want to emphasize that AST can never tell you a series decreases. If any of these things fail, the result is inconclusive. So like if the BNs are not decreasing, or if the limit of the BNs are not 0, we cannot say then that the series diverges by AST. In other words, AST can't tell you a series diverges. Failing AST is inconclusive. So if your series fails the alternating series test, either this isn't true or this isn't true, then you need to move to something else. You need to try some other test. Now the comparison tests won't work because these are not series of positive terms. In fact, the only other test that you can apply to the alternating series is the test for divergence at the moment, although there will be other tests that you can apply later. The test for divergence, remember, says if the limit of the ANs is not 0, then the series diverges. So I'll let you play around with that in this week's homework. But just remember, never tell me a series diverges by AST. AST is incapable of ever telling you that a series diverges. Okay, Zach, yeah, I'll grant the extension request. And anybody else who needs an extension request, of course, you can put one in, and I'll be going through and granting all of those today. Do make sure you're working hard on the homework. Last week's homework is one of the hardest homeworks in this class, and it's also one of the most important. This week, the only other major topic I have for you guys is 11.6, which discusses the root and ratio tests. Those are our last two convergence tests, and the concept of absolute convergence for a series, which is a new concept. After that, we're going to discuss section 11.7, but 11.7 is a lot like 7.5. There's nothing new. It just talks about how to put all the stuff from the previous sections together. So on Wednesday, I'm going to go through section 11.6. Friday, we will talk a little more about 11.6 and a bit about 11.7. Then the following Monday, I will assign you your study guide for exam 2. Now, it's actually the case that we might be able to move a little quicker if we wanted to. I could assign the study guide this Friday. Oh, no. Yeah, that's right. We were going to send out the study guide today. Yeah, so we want to do it like this. We still have to cover one more section, 11.6, before we're ready for the test. So what I will do, we're going to need just one more day, aren't we? Yeah. So I'll send out your study guide on Wednesday. All right. I don't want to do it today because I want you guys to be able to work through the current homework set, the appropriate homework set for this week, unless, well, we could send out the study guide and just call that the homework for this week. That's an option too. No, because that's going to reach through too much stuff. Yeah, okay, so today I'll publish one more homework, and then on Wednesday, I'll publish your study guide. And then your exam, we could either do it Monday or Wednesday of next week. All right, so I think the original plan was to do it on Monday of next week, and I still kind of like sticking to that because we need the time. The end of the semester goes very quickly after November begins. So yeah, we're gonna keep exam 2 on the date that I specified in last week's lectures. Exam 2 is going to be 11/2, 1 week from today. And so I might as well publish the study guide today. I'll go ahead and do that. So exam 2 is 1 week from today. Study guide 2 and homework 9 will go up today. All right, that's how we're gonna do it. So exam 2 is Monday, 11/2, which is what I was telling you guys in the recorded lecture videos from last week and the week before, and we talked about it. I think it's wise to keep that on track. That way we have enough time to cover the last few topics in the course. Because once we get into November, things go very quickly. So exam 2 is going to cover convergence, right? Section 7.8, 11.1, 11.2, 11.3, 11.4, 11.5, which is what we talked about today, and 11.6, which we're going to talk about on Wednesday. And that exam will take place during class time, Monday, November 2nd, 1 week from today. Okay? So we're going to keep it on track like we were discussing last week. Any other questions for me before we sign out? Alrighty then, I'll either see you in office hours this afternoon or office hours tomorrow, or I'll see you in class on Wednesday. I hope you guys have a lovely rest of your day.